Hello, welcome to Maths with EJD. In this video, I'll be talking about Euler's theorem, which is one of the basic theorems of graph theory. Euler's theorem is actually connected with the ideas of Eulerian paths and circuits. So let's look into this. Euler's theorem is essential in understanding what we call Eulerian paths. Eulerian Let me even say Eulerian. Okay, yeah, Eulerian circuits and paths, Eulerian circuits and paths, okay, which have practical applications in fields such as logistics, network design, and circuit routing. Okay, so let's talk about Eulerian circuits. So Eulerian circuit, what is that? So Eulerian circuit, an Eulerian circuit is a cycle. By now, we already know what a cycle is. A cycle is a closed loop. It is a cycle that visits. It's a cycle that visits every every edge of a graph, of course, exactly once, and returns to the starting vertex. To the starting vertex. The conditions for an Eulerian circuit, the conditions for an Eulerian circuit are one, the graph must be connected. The graph must be connected. So when we talk about a graph being connected, it means that you can reach any vertex of the graph from any other vertex. Maybe even if it is both directly and indirectly. So there's a path you can follow to get to any particular vertex without, jumping, without leaving the graph. Okay. Of course, except if they are isolated vertex of the graph. So in that case, but as far as for any path that is not isolated, you can reach any vertex. So the other thing is that every vertex must have every vertex must have an even degree. Okay, every vertex must have an even degree. Okay. Mm, well, I think this is a nice place to introduce an example of what this may look like. So imagine this example. So let's consider a graph with vertices v equals a b c d, our usual a b c d, and edges edges e equals a b b c c d d a d a. Yeah, even just this, right? Mm, yeah, let's stop at d a. Yeah. So. Now let's draw that to see what it looks like actually. So imagine you have A, B, C, A, B, C, D. So then you have edge A, B, you have edge B, C, you have edge C, D, and you have edge D, A. Now in this case, you'll discover that the degree of A is 2, two has, vertex A has two edges. Okay. I mean, it's connected to two edges. Maybe that's a better way to look at it. Um, then the degree of B also has two edges. The degree of C has two edges, just like degree of D. So in that case, one condition for an Eulerian circuit is that every vertex must have an even degree. So two is an even number, right? So all the all the all the vertex has a degree of two because they are all connected to two edges. So that's one condition. The other condition is that the first condition is that the graph must be connected. That means that you can actually reach, so you can easily move from A to B, you can move from A to C, you can move from you can't move from A to C, but you can actually follow the path from A to B, then to C. Or you can go from A to D and land at C. So that means it's actually connected. So the idea of connectedness is different from the idea of completeness. So a connected graph is a graph in which you can reach any vertex through either directly or indirectly from every other vertex. But a complete graph is a graph where you can reach any vertex from if you can reach every vertex from every vertex. That means there's a direct connection between every vertex and any other vertex you pick. So those are like two different kinds of graphs that we need to pay attention to. So you see that this graph now, so we can say that so we can say therefore the graph the graph the graph is the graph um okay, yeah, I'm looking at the right way to describe it. So the graph has an Eulerian circuit. The graph has an Eulerian circuit since it is connected, since it is connected, and each vertex has a degree of 2, which is even, right? So two conditions, the graph is connected, and of course, each vertex must have an even degree. So that makes it an Eulerian circuit. So that is a very perfect example of an Eulerian circuit. All right. So let's move on to talk about um, the Eulerian path. What does that mean? So let's do that. So imagine you have, okay, this is talking about Eulerian path. Okay. So for the Eulerian path, right, we say that an Eulerian path, or should even be an Eulerian or a Eulerian. I think it's more like a Eulerian path visits every edge. It visits every edge. Now, talking about the idea of visiting, right? I think we said something about visitation for the circuit. An Eulerian circuit is a circuit that visits every edge exactly once and returns to the starting point. So any starting point you pick, if you start from A, you can go, 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 and return there without taking one route twice. Okay. Then another way, if you take B, you can go, 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 and return to where you started from. That is a circuit. Then here you can start if you start from D, you can go to A, come to B, and then return. Go to C and then return to D. So that is a circuit. But in this other case now, see what happens for a path, right? So an Eulerian, let me stop saying and. A Eulerian path, a Eulerian path, right? A Eulerian path visits every edge in a graph. It visits every edge in a graph exactly once. Okay. exactly once. Now, the difference between a Eulerian circuit and a Eulerian path, okay, the difference between them is that for the Eulerian circuit, it returns you return to where you start from, but for a Eulerian path, you don't return to where you start from, basically. So for path, you just take every edge. It's more like just look at this now. Imagine that A, B, C, D are four different cities. So you start from A, maybe you live at A, right? And maybe you have a message to deliver to every other city. You live in city A and you have a message to deliver at city B, C, and D. And then, of course, when you're done, you go back home. Or you fly to from point A to point say you fly from point A to point D via B and C. Then of course by the time you're done with your business, you also have to go back, you know. Of course, but okay, I think the return flight thing won't really work. It's more like because you have to travel each road once, you don't have to take another a road twice. So that's what I demonstrated before. So you can fly from A, which is your house, you get to B, then go to C, go to D, and then return back home. Basically, that's the idea of a circuit. But in the case of a path, right, you don't go back to where you started from. That's the difference. So a Eulerian path visits every edge in a graph exactly once. So the conditions, the conditions for a Eulerian path for a Eulerian path are the first thing, the graph must be connected. We already know that the graph must be connected. Okay. Just like what you have for a Eulerian circuit. Then the next thing is that the graph now, this particular graph, the second condition for Eulerian circuit is that each vertex must have 2 degrees. I mean, must have even degrees, not necessarily two. The degrees of each vertex must be even. So here, the graph must have exactly 2 vertices. It must have exactly 2 vertices with an odd degree. 2 vertices must have an odd degree. What that simply means is that if you consider it as a directed graph, it means that you must have 2 vertices where you just get into them, you don't get out of them. You either get out of them or get into them, you don't do the two at the same time. Or or if you get in twice, you can only get out once, something like that. So the graph must have exactly 2 vertices with an odd degree. That means that the path will start the path will start at one of these vertices. The path will start at one of these vertices and end at the order. So you don't so unlike for circuits where you go back to where you started from, here you just travel all the roads and you don't go back home. You don't go back to where you started from, so to speak. Not necessarily. So in that case, of course, that won't be home because you can't go back there. So the path will start at one of these vertices and end at the other. And that is why you must have exactly 2 vertices with an odd degree. Now, if you look at what we had as circuit before, in this case now, we can consider that maybe one edge of what we had in the circuit is removed. So let's just take that example. So look at this now. Imagine a graph. Consider a graph with vertices, V, which is a collection of A, B, C, and D, and edges. Now the edges are not like what we had before. So let's say the edges are now A, B, B, C, and C, D. Only this. So now we have removed, the other time we had A, B, B, C, C, D, and D, A. So now we no longer have D, A. Okay? So imagine we no longer have D, A. So if you want to represent that, so it means we have A, B, C, and D. And the edges are A, B, B, C, and C, D. That's all we have. Okay. So DA is no longer there. So you see here that the degree the degree of A is 1. It's only connected to one edge. The degree of B is 2 because there's so you have an edge from A and you have an edge to C. Okay, so the degree of B is 2. Then the degree of C is also 2. You have something coming from B and something going to D. So the degree of C is 2, and then the degree of D is also 1. So we have exactly two vertices with odd degree, okay? So that's the so first of all, of course, the graph is connected in the sense that you can move from A to B to C and then to D. Then you can also trace it back. You can also move from C, D to C. So you can reach every point from every point. Okay? That's the idea, whether directly or indirectly. So, but the second condition is that you have exactly two vertices with an odd degree. So the reason for the oddness of the degree is that you either get into that vertex, or I mean you either get into the vertex once. I mean you just get into the vertex and not leave, or you leave the vertex and not come back into it. So that we can guarantee that. Okay, for instance, here now, the ones with degree edge A, I mean vertex A and vertex D have degree 1 each. That means you can start from D and end up at A, or you can start from A and end up at D. So this way you have guaranteed that all the if the routes of if the routes connecting A, B, C, D, they are just three. So the idea of the path is that you just take each road once without repeating anyone, basically. So that's what is happening right there. Okay. So for the circuit up here, the other time, right? You can move from A to B. Let me see. How can I do this? So you can move from A to B to C to D and then back to A. But in the case of this path now, you can not return to A. So you can move from A to B to C to D, and that's all and that's all you have. You don't go back into A, and that is what makes it a path. So can we see some practical applications of Euler's theorem that talks about Eulerian circuits and paths, right? I'll just list them and just talk about them one after the other. So, um, okay. But before we even go into this, let me see. I think there's something like an Euler theorem. Okay, good. Um, okay. I think it's important to just to emphasize that first. So let's talk about the Euler's theorem proper. Euler's theorem. That's the key thing, in fact. So the first thing is that a graph has an a graph has a Eulerian circuit. A graph has a Eulerian circuit if and only if and only if it is connected, if and only if it is connected, and every vertex, I mean, we've said this before, but we are just crystallizing this. If and only if it is connected and every vertex has an even degree, and every vertex has an even degree, and we've seen the example of that. Then the other point is that a graph, a graph has has a Eulerian path. A graph has a Eulerian path. Okay. If and if and only if it is connected, it is connected and has exactly two vertices of odd degree. So that is the two parts of the Euler's theorem, you know. So again, let's talk about the applications. So applications of Eulerian circuits and Eulerian parts. So the first one is postal delivery, right? Postal delivery. So just like I said the other time, if someone works in a post office or you work in a place where you have to service a particular location, so if you can get the Eulerian circuit, it's you. I mean that's the best way to travel your area, So that would ensure that you don't have to take a route, you don't have to take a particular road twice, so that, I mean, that way you save time. So it's some kind of optimization situation. So postal delivery and garbage collection, right? Postal delivery and garbage collection. You want to make sure that you travel through the city where you deliver mail or you collect garbage such that you don't travel any road twice. So in logistics, right, Eulerian parts, I used to design routes for postal delivery or garbage collection. The goal is to visit every location exactly once and return to the starting point, minimizing the number of turns and repetitions of parts. For example, a garbage collection truck must follow a route that visits every street in a neighborhood exactly once. You don't repeat it. You don't repeat any journey, so to speak. Then, of course, you have the circuit board design. This is bordering on electronics now. So you have circuit board design. So in electronic engineering, right, Eulerian circuits are used for routing the electrical connections on circuit boards. The goal is to minimize the number of traces needed to connect all components, ensuring each connection is made exactly once without retracing steps. Okay. So you see Eulerian circuits and path being really useful in this case. Then you have computer network design. So one particular area where graph theory and network theory are really important will be in computing, right? Like in networking and all that. So networking design. So Eulerian paths are applied in designing efficient data transmission routes where packets of information must visit each node or edge exactly once without revisiting the same path. These concepts can be used to reduce network congestion and improve speed. So you see, these things have practical applications. All right. So if you do if you have something to do around logistics and all that, understanding properly this idea of Euler's theorem uh, concerning Eulerian parts and circuits would actually be really useful in making your work more efficient. So in the next video, I'll be talking about the last part of the basic theorem, which borders on the Dirac's and Euler's theorems relating to Hamilton cycle. So if you have not subscribed to this channel, you want to do that right away and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment to let me know if there's a topic you'd like me to teach or a problem you'd like me to solve, and then like and share so that more people can have access to this great content. Till I come your way again, keep networking. Bye.